right. 11:57. So we got 3 minutes. I think we're in chapter 2 now, right? So we don't really need to work on. We need to start doing more problems. Yeah. So we're gonna switch to this thing over here. All right, so let's get started. 12 o'clock, 12:01. All right, so let's consider this problem right here. Okay? And y'all get a roll started from the please. All right, so in good weather, drive from Seattle to Spokane. Drive from Seattle to Spokane is Spokane, Washington. Interstate 95 hours and 51 minutes at an average speed of 105 kilometers per hour. In winter, it is not unusual to average only 80 How long would the trip take at this average? All right? That's the question. Anybody got any ideas about how we solve that? So what are we looking for? Looking for time, right? So we're looking for time, right? One, looking for time. Okay? That's our question. And our time scale is hours, right? And 3 is our givens, right? What are our givens? So we have, yeah. We have more than one speed though, right? Yay or nay? So we have a V1, we're gonna call V1 105 kilometers per hour, and V2 is 80. Alright, so V2 is going to be 80. What else we got? Huh? We got a time, right? We got time for the first part of the trip. Or we got time for the trip when it was in good weather. In good weather, we know it takes 3 hours and 51 minutes. What about in bad weather? Huh? We don't know. That's what we're looking for. So, 4 is to draw a diagram. We're not going to draw a diagram, right? We don't need it. 5 is to write down the physics. So what equation do we need to know? What's the first equation we talked about? Speed equals what? Speed equals distance over time. So speed, V, equals X over T. Right? So, according to the context clues, right, this speed, right, 105 kilometers, it took 3 hours and 15 minutes to cover this distance, right? When it was raining, it was this speed, because we had to slow down in the rain, right? We slowed down from 105 because it started raining, we slowed down to 80, right? Did we cover a different distance or we covered the same distance? It's the same distance that we're covering. The only difference is one is good weather, the other one is what? Raining. So we can set up an equation, right? We can say that, because we know this is the general form, right? V1, X1, T1, right? Well, this is also true for what? V2. V2 is also what? X2 over T2. And we know that X1 and X2 are what? The same thing. Because we cover the same distance. So now I'm going to rearrange these equations for X, which will give me what? V1, T1 equals what? Huh? Equals, no, not X1, huh? No, this is, remember, we're rearranging this equation for X because they are the same. So then this is X2 on this side, but what is it here? What is X2? V2 times T2. So therefore, our final answer is what? T2 is equal to what? V1 T1 divided by V2. Y'all following what I just did? So now I got an equation for T2. V1 T1 all over V2. And I got to make sure my units are all right? So I would convert this to hours, completely hours, right? So this is what? 3.51 over 60, right? So that's going to give us, well, what's 51 over 60? Divide that on your calculator. 0.85? So that's 3.85 hours. Right? So T1 can be written as what? 3.85 hours. And we got these in hours, we got these in kilometers, so now we can just plug and chug. T2 is equal to what? V1 is what? 105 kilometers per hour. T1 is what? 3.85 hours divided by 80. What's that answer?
5.05.
What? Hours. So T2 is 5.05. That's good enough. Hours. Now, does that make sense? Tell us why it makes sense.
Because it's more than the original time.
Right. You had to slow down in the rain. You took longer. Okay? All right. That was good. Of course, the problems on mastering are not this complicated. We don't have this much detail. So they're just to get you warmed up, you know. Let's see. I think I did this one the other day. Yeah, I did this one the other day. Alright. Let's see. Alright, let's go back to one we've already done. And I think hopefully you're going to grab a hold of this one really quick. And I won't have to say much. A rock. Oh, that green is really light, huh? Can't see things. I can barely see that. Rock. A rock is dropped. A rock is dropped. Yeah, so so today is Friday. So let's take our first exam next Friday. Okay? Because the following week I will be gone. Alright? So next Friday we're going to take our first exam on 1 and 2. Chapters 1 and 2. Alright? About 5 questions, kind of like what we're doing right here. Same deal. Alright? 20 points apiece, 100 points. A rock is dropped from rest, from the Golden Gate Bridge. And I'll put some practice problems on chapter 2 this weekend. Golden Gate Bridge. Okay. How far will it have fallen? Will it have fallen I think we did this already. Well, do it again. Falling after 1 second, 2 seconds, 3 seconds, and 3 seconds. And how fast will it be moving at each instance? All right. gonna do?
How high is the Golden State Bridge?
Well, we don't need to know that.
Okay, and that's the rock. No, it's
9.8, right? So first let's do like we always do, and we follow the problem solving procedure. What's the first step? Huh?
What you're looking for.
What's the problem? So what are we looking for?
the distance in
Dis-
seconds 1, 2, and 3, and the velocity at also all these important times 1, 2, and 3.
Okay, distance at 1 second, 2 seconds, 3 seconds, and velocity at 1 second, 2 seconds, 3 seconds. Yeah. And what's the second step? It's the time scale, right? And in seconds. So, right? Everything is in seconds. So we don't have to worry about a conversion in time. Right? 3 is what? Givens, right? What are the givens? Gravity.
It's on Golden State Bridge, unless it's the same.
Gravity. You're dropping it from the Golden Gate Bridge. Starts from rest. So V, so knot is equal to 0 meters per second. What else? Is there anything else? No. You don't need to know math. Right? 4 is a cartoon or diagram. We don't really need that. We can visualize that in our head, dropping something off the bridge. Right? NA 5 is the physics. So what's the free fall acceleration? What's the equation? So y is equal to 1/2 GT squared. Right? So what that means is we just do what? 1/2. All right? And because G is pulling us down and the object is going in the same direction with G, we're going to make it the same. But some people will write G as what? Negative. Okay? But here, we're calling, when the guy is holding it here, that's 0. So when he lets it go, it travels a distance down because of gravity. And gravity's pulling it the same direction as the distance is traveling. So it's positive. All right? So 9.8 meters per second squared. And now we just do what? Plug in the times, right? 1 second, right? 1/2, 9.8 meters per second squared. 2 seconds, and 1/2, 9.8 meters per second squared. 3 seconds.
I got a question.
Yeah.
So, you put the half, no, my question really is, so why you didn't make it,
Why I didn't do what?
why you didn't make it, the red?
So when you dropping something, so we start at, so if I'm dropping something, right? This is my 0, right? And when I let it go, right? Because we're trying to measure the distance, right? If I let it go, then it's gonna cover a distance what? Down, right? Because the gravity is gonna pull it down. So because gravity is pulling it down and it's traveling down in the same direction, then the gravity is the same sign. So imagine if it was going up, but gravity was pulling it down. So you see how, in that case, you would have gravity as negative because it's going against your motion. In this case, I'm dropping it off the Golden Gate Bridge. So when my object starts to move, it's going to move in the same direction as gravity. So that's why they're the same. That's why it's positive here. So what are these numbers? Anybody got the numbers?
Let's see, for the first one, 1 second, 4.9 meters per second.
Wait.
Let's see, that's,
No, we're looking
9.8.
for a distance.
Oh, distance, oh. I don't have distance.
4.9 meters.
Meters per second.
No, meters per second is the speed.
Oh, wait.
We're calculating the distance. Why?
Because when you square
You got, this got to be square, right? Sorry about that. I ain't write that here. I wrote it there, but not here. So when you square it, it's going to end up with what? Meters. 4.9 what? Meters. What's 19.6 meters? 44.1 meters. Now you can see how this is exponentially increasing. Or it's not increasing at the same rate, right? It's accelerating. You see that? Because if it was increasing at the same rate, then after 2 seconds, this would be what? 9.8, right? 4.9 times 2. If it was moving at the same speed and wasn't accelerating, this would be 9.8. Then this would be this times 3. See what I'm saying? But because it's accelerating, it increases drastically. All right, so that's not the end of it, right? What's the second portion? Now we got to find the velocity at each second. All right, so let's write it right here. Right? So what equation are we going to use? Yes, right? So we know that what? We know that acceleration is equal to what?
9.8.
No. What's the equation?
Final velocity
Final velocity
minus initial.
minus initial over what?
2 times.
No. Over t, right?
Okay, yeah.
Right? And so if we rearrange this equation, then we can do this, right? V final is equal to what? V naught plus a t. And we know that V naught is what? Huh? 0, because we dropped it. So then V is equal to what? A times T. And we can plug that in, right? 9.8 meters per second squared and 1 second. 9.8 meters per second squared and, oh no, not squared. And 2 seconds. Right? 9.8 meters second squared, 3 seconds. What are those numbers? We're starting to get a little
19.6 and 29.4 all meters per second.
all right.
It's not. It's a vibration.
Yep. 9 point. So this one is 9.8, right? 9.8 meters per second. What is it? 19.6
Yeah. And
meters per second.
29.4.
And 29.4 meters per second. So that speed is drastically increasing, right? Or increasing at the rate of gravity. It's accelerating. What time is it? What's the time we got now? What is it?
12:30.
28. All right. Maybe we got time for one more. All right, so this is a matter of practicing, folks. That's what this is. You gotta practice this. You don't get good at it just from nature, from being good at math. You don't get good at this. This is applied mathematics. All right. Oh shit. I gotta erase it. There we go. All right. Last one. All right. Well, I ain't gonna make y'all deal with the quadratic equation just yet. Not yet. Let's see. The Earth travels in nearly circle orbit. No, we haven't gone over that yet. A driver traveling. No. Okay, it's a good one. All right, a typical. typical jet. A typical, where did I see that? Okay, typical jetliner. Jetliner lands at a speed of 100 meters per second. That's like 22 miles per hour. Oh no, I thought I was looking at that wrong. I said, boy, that's slow. 224. I was saying, I know that no plane will land at 22. I'm getting old, my eyes getting weak. While braking.
And words might be too little.
Say what?
And words might be too little.
Yeah, that's true too. While braking, it has an acceleration of negative 5.2 meters per second squared. So we know it's doing what? Slowing down. It's a negative acceleration. And plus it's landing, right? So the first question is, how long does it take the plane to stop? how long does it take the plane to stop? So how we gonna solve this one? Huh?
We know 100 meters per second, that's where it's landed, so that's the V naught. And we know the acceleration, so that's all we need to know.
All right.
We just can find the time.
All right, good. So let's go through problem solving.
And it stops.
And it stops.
Feedback, so that's the final velocity.
That's the final velocity, right? So let's do this, but let's go through problem solving procedure like we always do. What's the first step? What are we looking for? Huh? Time, right? Time. Okay. What's the second step? Oh, and we got a second question to it too, I think. What's the second question? 321. 321, second question. What's the minimum? Oh, yeah. So we need to know what's the minimum length of the runway too. What is minimum length of runway? What is the minimal? What is the minimal length? What is the minimal length of runway? Okay? Question. Alright, how long is the question? Okay, so first step, right? And let's make it quick because we gotta go. How long does it take to stop? We're talking about time, right? Right, and then for B, we're talking about what? Distance, right? Distance. Okay, so 2, the time scale, seconds, okay? 3 is givens. Okay? What are the givens? I got acceleration of -5.2 meters per second squared. What else we got? Huh? Initial velocity is what? Huh? 100 meters per second or 224 miles per hour, right? But we're gonna use the meters per second. Okay. What's the final velocity? 0. Plane gotta stop, right? At the end of the runway, it stops. Right? So we don't need to draw a diagram for this. 5. Right? What's the equation? Easy, right? Not the golden rule. We could use the golden rule, but we got one even easier than that one. Right? Because we got everything, he just said it, right? We got the final velocity, we got the initial velocity, and we got the acceleration. So, yeah, it's just A equals what? V final minus V initial over T. So we just swap those two. T equals what? V final minus V initial over A. So then I'm gonna have what? Final is 0 minus 100 meters per second. All of that over what? -5.2 meters per second squared. What's that number? What is it? 19.23 what?
So we know
Seconds. So about 20 seconds. Yeah, I guess so. About 20 seconds. When you landed the plane. Yeah.
Only one plane after the
So let's deal with the length. Right? How can we find the length? What'd you say it was? Golden rule. So let's get the length from the golden rule. And what did we say the golden rule was? And I'm gonna erase this at the top. What did we say the golden rule was? Yes. Yes. That is the golden rule. Final velocity squared minus initial velocity times 2ax. And in this case, what is x? That's the distance we need for the runway. So we just rearrange this. So we're gonna have x equals what? V final squared minus v initial squared all over what? 2 times a. And we know our final is 0 meters squared minus 100 meters per second squared. All of that in one bracket, right? And 2 times what? Negative 5.2 meters per second squared. What's that length? Got it? What you got?
9.62 meters.
Oh, not 9.62. You know, the plane can't land in 9.62 meters, right? That's close though. You just got your decimals off. 962 meters. Right? So you should have known, right? What's your name in the pink?
Sydney.
Sydney. So when you said 9.62, right? You should think in your head. You say, okay, well, can a plane, a jetliner, land in 10 meters? Not likely. So something went wrong. You probably just had a decimal issue, right? So this should be 962 meters, about 1,000 meters. So let's convert it. Let's convert this to feet because we know what feet are, right? Somebody help me convert this to feet. Where am I gonna go to first? Centimeters, right? So 1 meter is what? 100 centimeters. Now what? Inches. 1 inch is 2.54 centimeters. Now what? 12 inches in a foot. We know how much feet. We know feet, right? So what's this? This is gonna tell us how long the runway should be in feet, which we have a good idea of how long that is.
Yeah, so there's 56 feet.
3,156. So 3,000 feet. Runway should be about 3,000 feet. How long is what is a football field? 100 yards. So that's what is that? That's 300 feet. A football field. Yeah, and a runway is much longer than a football field. It's a fewer than football fields, right? Yeah, a runway is long. Very long. You need a lot of space for an airport, right? So that sounds about right. About 3,000 feet for the plane to stop. All right? All right, folks. So we're gonna keep on practicing like this until next Friday, and we're gonna take our first exam on chapters 1 and 2. And we're gonna maybe well we'll review Monday and Wednesday.